not try infinite different combinations in order to see which one works better. So finding the number of topics is a challenge, and it's a hyperparameter. So the probability of topics and the proportions and the assignments given the documents. This is the probability of beta and z and theta given your documents. Because document is just a set of words. So what you should notice is that document is distribution over topics, and topic is a distribution over words. For example, distribution over words is P of beta given your word distribution. And the topic distribution over topic is theta given W. And this is done per document. For example, you have some topic words like a topic like cat, like dog, like politics, and so any of them has a different number. So it's a distribution. So assume n is the number of words and m is the number of documents. So we start with the traditional unigram model. So this is W, this is N. We have n words, we have m documents. So this is called a unigram model. And the words of every document are drawn independently from a single multinomial distribution. You know, multinomial distribution generalizes a binomial distribution, and probability mass function is just n factorial over x1 factorial, x2 factorial, xk factorial, and p1 to the x1 times pk to the xk. And notice that all of the xi sum to n. And so the probability of W is just the product. Naturally, it becomes the product of different words. So in real words, we have multiple topics, each of which has different word distribution. But assume that each document has one topic only. So we have Z, which is topic, and then we have word, and we have M documents. So each document is generated by first choosing a topic Z. This Z, you should first choose the topic Z, and then generating words independently from the conditional multinomial. So when I say W, it means W1, Wn. So it's a joint probability, and so summation is over Z, P of Z, n from 1 to n, probability of Wn given Z. So I give you an example. For example, in Iran, the inflation, people talk about inflation every day. And people talk about corruption as well. Corruption. Ideology and religion and those things that is mixed with politics and those things. But people usually don't talk about cats every day. Or they don't talk about mathematics, the beauty of physics, the great German physicists, the great French mathematicians, great Russian mathematicians. They don't talk about great Jewish computer scientists and Jewish mathematicians. They don't talk about that. So in Iran, unfortunately, they talk about inflation more than anything else. They talk about corruption. But in Germany, the distribution is quite opposite. They talk about great things like science, mathematics, physics, computer science, mechanics, Maschinenbau, culture, and physics. And they don't talk about inflation, they don't talk about terrorism, they don't talk about violence. So it's a great country. So Germany is a great country. And in economics, because it's a general things, you have to talk about all of those measures like poverty. So it's quite uniform distributed. Okay, so let's talk about PLSI. So we have D document. You have Z topic. You have word and words. You have end words, M documents. Same as before, you have M documents. But PLSI, what is the PLSI deficiency? Well, it has a giant matrix. The probability of your document is the probability of D times Z, probability of W and given Z, probability of topic given D, given document. So it has a giant matrix. So it's computationally expensive. If you pick a document that have not seen before, you have no idea how to model it. So it reminds me graph neural networks and those paradigms as well. For example, in GraphSage, that I will explain later, it's a graph node embedding method that even if you have not seen any training, any data before, you know how to model it easily and naturally. For example, in PLSI, that it has a problem that it's very expensive to compute. And if you have a document that you have not ever seen, then you don't really know how to model it. So LDA, linear Dirichlet allocation, so it imposes Dirichlet prior over unmodeled parameters. So alpha and theta and Z and W, and this is beta. So you have N again, and you have M, and you have alpha, but you have Dirichlet priors. So you have P of W. So theta is like, theta is assignment. It's like, for example, your topic could be about, it's a simplex. For example, you talk about cognitive science, this topic. Another topic is AI. So another is, for example, neuroscience. So any point inside this simplex corresponds to a different text. A text could be a mixture of these topics. So P of W is equal to integration over theta, because you could have any assignment. So you take an average of that, and then multiply n from 1 to n number of words, and Zn from 1 to k, you have k topics, and p probability of Wn given Zn times probability of Zn given theta times probability of theta alpha, and then summation over theta. And the Dirichlet distribution, so it takes k arguments. P of theta given alpha is equal to gamma of alpha I, and I from 1 to k, gamma of alpha I. So we usually say this is 1 over beta of alpha by definition. And beta is, beta function. Times theta 1 to the alpha 1 minus 1, theta k to the alpha k minus 1. Alpha is a hyperparameter, so if you have a simplex of k equal 3 topics, as I said, AI, cognitive science here, and neuroscience here, any point here is, so alpha k is equal to 1 if it's like that. But sometimes your hyperparameter could be very big. It means that it is concentrated in the middle of the simplex. And imagine that it is 3-dimensional. And sometimes your simplex, it is distributed at the corners. So at the corners, you have huge value, and in the middle, you have almost nothing. So this is AI, this is cognitive science, and this is neuroscience. So any point inside is just a combination of the 3 topics. And so it takes k arguments, alpha k minus 1. So it takes k arguments, and which sum to 1. And so think of the space of all multinomials as k minus 1 simplex. For example, here we have three topics, so it's 2 simplex. And the topic mixture proportion are drawn from some distribution. And notice that alpha is just the hyperparameter. And now we are ready to write this interesting measure. This is the integration over n from 1 to n, Zn, probability of Zn given theta, probability of Wn given Zn and beta, times d theta. So it's a mixture of unigram, let's say. This is the mixture of unigram. And the marginal likelihood is just the d from 1 to m. M is number of documents, integral over that. And so the goal is to estimate the hidden variables. So this is the probability of theta d given alpha. So this is the Dirichlet with hyperparameter alpha times the product of n from 1 over n of d is the number of words in document D. So n of d, it means the number of words in document D. And then it is just so the goal is to estimate the hidden variables. What we can do is use variational inference, which is on one hand it is not accurate. Unlike the MCMC, which I love, Markov chain, Monte Carlo, it's very accurate, but it takes time. But variational inference converges very quickly. So the distribution is intractable to compute in general. That's why we use variational inference. I mean, the probability of topics and proportion of words in assignments given your documents, which is W1, Wn. So this is the probability of beta and z and theta given W. And so the aim of variational inference, you take everything simple and decoupled, theta. So it's a very big simplification. That's why it is not accurate. But we need it. We are engineers, so we need to do something quickly and efficiently. I mean, the computational complexity should be very low in order to be scalable. So that's why we use this variational inference. In the next week, I may talk about node to vec, Siam-set network, triplet loss, few-shot learning. I skipped those things, and I like to talk about graph sage. So the important thing that we should talk is, so I talked about word to vec. So in NLP, these are very important. In NLP, I talked about word to vec, and I talked about LDA, and we have a combination of them, which is LDA to vec. So we need to talk about them. And then we need to talk about deep walk. So we use some random walk in order to, and give the random walk to the word to vec in order to, so this is the algorithm of deep walk. And the other thing is node to vec, which is much more global than deep walk. And then we have some convolutional graph neural networks, which has many problems, because for example, if you have unseen events, you have problems. You should give the adjacency matrix at one shot, and so it has some problems. That's why people invented graph sage, which is my favorite. I love this graph sage algorithm. It's very natural, and that's it. Those are the things that you need to understand from NLP, especially this one, which is very modern. And this one is not practical. You cannot use it in practice for large data, for big data. And node to vec, so it's a good inspiration for the rest of the articles. Deep walk is on top of word to vec. And so NLP is really interesting, but you need to overcome some problems of graph sage. Maybe we can do it in 2040 with some completely new paradigms. If we talk about graph limits, graphones, we need graphlets. But graphones is a natural things in order to talk about future technologies. We need to graph limit. For example, you have G1, G2, and the graph converges to some limit G. And so these technologies and paradigms, which are already discussed in combinatorics and mathematical departments, but unfortunately computer scientists are not aware of these important new paradigms that are essential for the future of artificial intelligence. And so So we need to talk about, for example, one of my favorite topics, if any of you is interested, we can collaborate, is if